So within this video, we're going to go ahead and look at our remaining set of Unit 1 notes, the origin of the Earth. And remember that these are all based off of scientific theories, based off of multiple collections of evidence over time. So let's go ahead and look at Introduction to the Earth. So we're looking at the theory of the Big Bang. So about 14 to 15 billion years ago, scientists believe that just this kind of large explosion happened in our atmosphere and kind of created, or in our universe, and kind of created this collection of dust particles and rock and sediment and stuff like that to actually create the Earth. We've also got our nebular hypothesis, which relates back to about 5 billion years ago. And the nebular hypothesis theory states that our solar system was formed from this rotating cloud of gaseous elements and compounds. So this matter all started kind of forming the sun due to this intense increased gravity, and it left small amounts of matter starting to orbit around this like central mass known as protoplanets. And protoplanets, of course, think of the word prototype, that is an early version of something. So this is an early version of our planets. So let's talk kind of a little bit about proto-Earth. It was intensely hot, and it was this contracted ball of hot liquid magma. When our proto-Earth started to form, the densest material was starting to move towards the center, which eventually is going to create our dense core. All right, so let's look at our habitable zone of Earth. So what exactly is this? And this is the distance from a star where liquid water can exist on a planet. So where can we find this? For us, it's about 93 million miles away from the sun. So let's just kind of look at a little bit of a fun fact, and this is an article from back in 2013, but there are 100 billion to 400 billion, and this is, of course, an estimate. It varies every single day as we start to see more stars kind of, and quote-unquote, popping up, or our light years are finally reaching us, stars in our galaxy. So just some extra information. In July of 2015, NASA announced that the discovery of the first near Earth-sized planet in the so-called habitable zone around another star is 1,400 light years away from Earth in the constellation Cygnus. Our Kepler 252 or 452b is the smallest Goldilocks planet to date found in a habitable zone, and NASA has said in a statement that of course, it needs atmospheric pressure strong enough to support liquid water on the planet. And not only is the planet in that zone, but it's also a planet and sun combination just like ours. So we've got our Earth and the sun. This one has a planet and sun combination as well. So is this habitable zone always in the same place? No. As the star gets older, it gets hotter. So this is starting to extend the habitable zone. So as far as you can kind of reach with that condition that is prime for the sustainability of liquid water. And is it the same for all life? So no, of course not. We know that down in the hydrothermal vents in the deep sea, these microbes that we have just on Earth can survive in much more extreme conditions. And we think of them as extremophiles. So what's Earth got on it that makes it so special to support all of this life? Well, we have abundant liquid water. 70% of our Earth is covered in it. We've got these environmental conditions that maintain liquid water. And our size, we got a long-term heat source. We've got incoming solar energy based off of this stellar evolution. Our oceans are going to start to regulate our global temperatures as well. So we're not getting a super extreme climate back and forth day to day. We've got the oceans kind of regulating that over time. So then we start to think about, well, if Earth is inhabitable now, were other planets habitable in the past? Well, they say that early Mars, and this is why we've been doing so much research and extending upon Mars, because they believe that there were large evidence of flowing liquid water. So we're starting to kind of look and see if life could actually have existed on Mars. We also had some of these warmer temperatures, so the heat from the interior would have been higher, and then we've got this warm climate coming from these greenhouse greenhouse gases or carbon dioxide clouds. So we can look at this and we can kind of think about it like, as I said, the Goldilocks zone. So we've got too hot, too cold, and just right. So Earth is in that baby bear area. So baby bear had his porridge was just right. So we can look at this picture right now, and I've kind of given you the answer up on the screen already, but what exactly is this? And it does not take any shape or form, does not even look like Earth, except for the fact that it is spherical. So we're going to kind of look at what Earth looked like 4 billion years ago, and as over time, we've kind of, our planet has evolved as well as the species on it. So we're going to go ahead and kind of look at the layers of the Earth. Of course, in our center area of the Earth, we've got our solid core. Then we come out to the outer core, which is slightly liquid. Then we're going to get up to our mantle, asthenosphere, lithosphere, and crust. And of course, this asthenosphere is where we've got that kind of movement of convection currents, which is, of course, moving our plates and leading into evidence for that theory of plate tectonics. So just one more time, it's kind of laid out on the screen for you. Our inner core is solid. It's made of nickel and iron. Our outer core is liquid, and of course these are very hot. Our third layer from the inside is the mantle, and it swirls and mixes like a boiling soup. So think about how water looks like it when it's boiling on the stove, where the bubbles come up and then move back down. That is our convection current. So it's also driving the movement of these plates. The asthenosphere is the portion of upper mantle that directly is beneath the crust, and this is where, of course, our convection currents are moving. Our lithosphere is actually where our tectonic plates are. So the asthenosphere is moving these parts of the lithosphere. Then we've got our crust, which is where we live, and then the biosphere is that living layer. So our crust is kind of our ground, biosphere is where we live. And we can kind of see a picture here of mantle convection, and of course I have posted the links that are within this PowerPoint off to the side, so you can kind of go back and watch some of these videos, which I strongly suggest. But if you look, we can see that we've got convection cells, they're moving up, they're rising, they're heating, and they're cooling. So they're going to start to kind of move this magma, this hot magma, and kind of move all of our plates. So let's look at our pictures of 4 billion year ago Earth versus today's Earth. So what's so different about this early Earth? Well, the atmosphere was definitely different. So our early atmosphere was made of very light gases, so hydrogen and helium. These were blown away very quickly. We've got wind, solar wind coming off, and this is starting to kind of impact the events on Earth. Our later atmosphere, which is what we are kind of living in now, is resulting from outgassing, and these gases are expelled while Earth was forming. So we've got lots of water in our atmosphere, a very, very heavy humid climate, and we've got lots of carbon dioxide, which of course is going to start to kind of add to these greenhouse gases. So let's look at some compositions of the modern atmosphere. So we've got gas, oxygen, argon, carbon, and carbon dioxide. So we're looking at our highest percentage of our atmosphere today is, of course, nitrogen at 78%. Our next highest is oxygen at 21%. And then, of course, we've got our 1%, which is made up of argon and carbon dioxide. And then we've got some other trace gases, which are very, very small numbers. I'm not going to have you memorize each one. So let's go ahead and look at how our oceans are kind of impacting our Earth. So as the Earth was starting to cool, water vapor in the second atmosphere condenses to the surface as actual water. So we've got our water cycle. It's starting to be all up in that atmosphere. Remember, we said there was tons of water vapor in the air. So it's starting to cool, fall, and sink in the form of precipitation. And we're going to end up getting all of these freshwater sources, our ocean sources, stuff like that. So we've got this rainfall, runoff, salts, all of these other things are being pushed into the ocean. So as our precipitation is falling, it's pushing all of these sediments back down into our oceans, kind of creating this salty oceans and seas that we can see. So let's go ahead and look at the physical geography of the Earth. So with Earth's surface, 29% of our Earth is landmass and about 70% is water. And a lot of times you'll see that as 70-30 just because it's easier to remember. Our northern hemisphere is actually very different than the southern hemisphere in relation to the percentage of water to landmass. So in our northern hemisphere, we have 61% ocean coverage, and in our southern hemisphere, we have 80% ocean coverage. And you can see this just by looking at a map. You can see where the layout of the continents are and just about how much water is located in each hemisphere. So let's go ahead and look at a map now like I was talking about. You can see the ratio of landmass being greater up in the northern versus in the southern. So we're getting a little bit more oceans going on in our southern hemisphere. All right, so let's look at our kind of intro to geography. Oops. And this is the last slide that we're going to get to in this video before it goes on to part 2. So there are how many large ocean basins in the world? We're looking at about 4 of them. So 4 main ocean basins. We've got the Pacific, Atlantic, Indian, and Arctic.